Yeah, good. Okay, so let's start. So CTL is about this branching time logic, whereas LTL was a linear temporal logic, right? So in CTL, as we'll see, looking at different kinds of properties that can be expressed using CTL but not using LTL, inherently because the reason being there are these branching time properties which you can express in CTL, but LTL cannot express or capture such properties. Okay, so yeah, let's start. And when we look at the specific examples, I think it will become clearer. Okay, so the syntax of CTL, we had like the state formula as well as the path formula. So are you all able to hear me properly?
Yes, sir.
Okay, good. So this, yeah, if you have any difficulty in hearing, just stop me and let me know. So the state formula has like it's of this form. Like you have the true, or there is an A which is an atomic proposition, then conjunction, and then you have the negation, and there then you can have there exists a path such that the path formula psi holds in that path. Then for all paths, the path formula psi holds in that path, and so on. Okay, so this is the sorry. So the path formula is like this. You have, so this is just similar to LTL. You have next of phi or phi 1 until phi 2. Okay, and then as you see here, that you have the state formula, and then there exists, and then there is a path formula, and in that path formula you have like next or until, and then there you have a state formula. So the state and the path formula, they alternate. Okay, so we looked at all these things, and similarly you can also have eventuality, just in the same way as you'd express these things in LTL in a very similar way, right? These derived operators. So the eventuality and the globally, the always properties. Okay, so uh, yeah, we also looked at some of the uh, properties which can be expressed in CTL, right? And all these things we looked at, and um, then the CTL, the semantics is given on a particular on a Kripke structure, and so every logic has a syntax and the semantics. So the semantics, it's described with the help of a Kripke structure. Sorry. And if I have something like there exists this psi, such a state formula, then it essentially means that there exists a path pi such that pi satisfies psi. And if the state S satisfies for all psi, if and only for all paths pi that start from S, for all paths pi starting from S, we have that pi satisfies psi. Okay. So that is the thing. And for the path formula next of phi and phi 1 until phi 2. So this is exactly as in the case of LTL. Okay. And we also looked at some of these examples, right? Like, for example, if you see, let's say, along all paths, gray until black. So indeed, along all paths, you have gray until black and so on, right? So this is, so we looked at these things. And then we also said that uh, just like LTL, here also we can have an existential normal form for CTL. Now, just to note that for the existential normal form, we need something like this, that there exists globally phi, there exists always phi. So this operator exists G is something that we need. Why is it so? Because if you have for all x, for all next phi, then the for all here can be replaced with, it's not the case that there exists a path such that next of negation of phi, right? So Um, just one thing we should note is that the negation can be applied only on the state formulas. Clear? And if you have, let's say, for all phi 1 until phi 2, here I think if we look at this, so it is like it's not the case that there exists a path in which negation of phi 2 until negation of phi 1 and negation of phi 2, as well as we want this condition, which is that it's not the case that there exists a path such that always negation of phi 2, right? So because of this expansion, this equivalence here you see that whenever we are going to get rid of the for all until, we need such an exists G operator. Clear? Uh, so that's why we have this exists G. Okay. And in general, like as we have seen earlier also for the case of LTL, the translation from CTL to existential normal form, it may cause an exponential blow up. And similarly, for all F, for all G, all these things also you can have like, you can essentially have the write them in the ENF, existential normal form. Okay, clear? So any question on these parts so far?
No.
Okay, good. So now we also looked at the positive normal form, and the positive normal form, if you recall, there was this, we had the, yeah, um, so I think here we have, we have pretty much, like I don't separately, um, okay, so here, um, so the thing is that in the state formula, in the positive normal form, what we have is that the negation is allowed only on the propositions, okay? And the path formulas, they remain the same. In the path formulas, if you recall, even in the standard CTL, we don't allow negation on the path formulas directly. So the negation was on the state formulas. Here we are saying that the negation is only on the proposition. So and the uh, path formula, it essentially it remains same. Uh, okay. So I think here I should ideally, like it should be some kind of a psi where I use the psi for the path formulas, and for each CTL formula, and this psi, the path formula, it remains the same. Okay. Now, uh, essentially we can see that whenever the formula is of this form, I can always push the negation inside and I can get a positive normal form. But here also, uh, I mean, when we are using the positive normal form along with the until, we also need a weak until. Okay. So we also have the weak until in the positive normal form, and the what it can result into is that again there can be an exponential blow up, right? So this kind of things we saw when we translated LTL formulas also into their positive normal form. So in order to avoid such exponential blow ups, what we also had were these release formulas, right? So the release was one thing with which we could avoid this exponential blow up, right? So this is the thing. So now, uh, for a given formula phi and a Kripke structure K, uh, so how do we, so now we are looking at the model checking. Okay, so how do we do the model checking? Essentially, uh, we have to, given a CTL formula phi, the idea is that, and we are also given a Kripke structure K, right? And we would like to see, we would like to check if K, which is the Kripke structure, it satisfies the CTL formula phi. Okay. And the way this would be done is essentially we look at all the states in which the formula, all the states that will satisfy the formula phi, all the states of the Kripke structure that will satisfy the formula phi, and then you see, check just if the initial state of the Kripke structure, whether it satisfies phi or not, right? So what we compute is something called SAT of phi. What is SAT of phi? SAT of phi is precisely the set of states such that it's the set of states, it's the set of states or the worlds um, is belonging to W such that S satisfies phi. Okay, so this is what we are going to compute and then see if the initial state of the Kripke structure, okay, the initial state of the Kripke structure, does that belong to this SAT of phi? Okay, clear? Now, in order to compute this set, SAT of phi, we'll look at all the different subsets, all the different, or rather, all the different subformulas of phi, right? Different subformulas of phi we will look at. And for each subformula psi, let's say for each subformula of phi prime, we'll compute SAT of phi prime. Okay. And this is, in some sense, if you recall that we can express the, we can express essentially a formula phi using its parse tree, then we solve the SAT, the satisfiability set, starting from the bottom of that parse tree, starting from the leaves. And so for each leaf, which may be a just a proposition in itself, right? For the so for this, for the proposition itself, we compute what is the set of states which satisfies that proposition, and then as we go up the tree we build the satisfying set for each of the subformulas. Clear? So that's what here I'm writing, bottom up traversal of the parse tree. Okay, and the nodes of the parse tree represent the subformula. Okay, so the inner nodes are labeled with an operator. What kind of operators? In the existential normal form, you have this kind of things: exists x, exists until, or exists g. Okay, as well as the negation and then conjunction. Okay, and so SAT of true, if you have SAT of true, this is the entire state space W, entire set of worlds in the Kripke structure, which is W. SAT of A is essentially the set of states such that A belongs to the label of the set of propositions which occur in state S. Then that is SAT of A. Okay, the set of states such that A occurs in the propositions that appear in that state S. Clear? SAT phi 1 and phi 2 is like if you have computed already SAT phi 1 and if you have computed SAT phi 2, then the intersection of them you will get SAT for the SAT phi 1 and phi 2. Okay, SAT negation of phi, similarly it's just that you compute SAT of phi and it's a complement of that set is the SAT of negation of phi. Now what about SAT of exists x phi? How do you compute that? So first, let's say we have computed SAT of phi, right? So what is exists x phi? So it means those set of states, right? Those set of states such that there exists some path, so there exists some successor which will satisfy phi, right? So some successor that belongs to SAT of phi, correct? Okay, so that's why, so this SAT of there exists x phi is essentially the set of states such that post of S intersection SAT of phi is not empty. Is it clear? Post of S. What is post of S? It's the set of states that you can reach in one step, the set of successors. So as long as uh, the set of successors intersection set of phi, so there should exist some state, some successor state, which belongs to the set of phi. That's the idea, right? So post of S intersection sat phi not empty. Okay, so such states should belong to sat there exists x phi. Clear? Is that okay?
Yeah.
Yeah. Okay. So now what about exists phi 1 until phi 2? So now we are saying that this is the smallest set. Okay, it will be clear why we are saying this is the smallest subset T of S. So initially, so suppose, okay, so maybe you can tell me like why. So suppose you have to compute this. What does this mean? So it's a set of states such that there exists a path, there exists a path, and somewhere down the line, you should see a state that satisfies phi 2 while going through states which satisfy phi 1, right? That is what it means. There exists a path such that you can reach a state in that path which satisfies phi 2 while going through states that satisfy phi 1. Now, how would you compute this thing? Can someone say, how would you like to compute such a path? Given that suppose here we have already computed sat of phi 1 and sat of phi 2. Suppose we have already computed these two, sat of phi 1 and sat of phi 2. So how can I compute exists phi 1 until phi 2? How can I compute this path?
So basically, either the formula should currently satisfy phi 2,
Yes.
or if it does not, or it should satisfy phi 1. And then in that case, we will compute the sat of there exists phi 1 until phi 2 of all its neighbors, not neighbors, successors.
Mm-hmm. So
And yeah,
you will compute it one step at a time, right? So first of all, you see that if there is a state which satisfies phi 2, then it will anyway be inside this set, correct? If there is a
yeah,
say, if there is a state which just satisfies phi 2, it will be inside this set. Is it clear?
yeah,
Right? That there exists. So if I have a state which satisfies phi 2, correct? Then this state satisfies phi 2, suppose S, right? Phi 2. Then S also belongs to sat of there exists, there exists phi 1 until phi 2. Clear? So this is this clear? Like if a state satisfies phi 2, then it anyway belongs to sat of exists phi 1 until phi 2. Correct? Because there is already a state. I mean, if I'm here, then I already have a path which is satisfying phi 2 immediately, right? So it satisfies there exists a path satisfying phi 1 until phi 2. Clear? Is
yeah,
that okay?
yeah,
And now what we are saying is that uh, now in order to compute the remaining states, so already suppose I say that sat of phi 2, right? So I say that initially to start with, my sat of phi 2 is a set T. I call it T. Okay. Now I will see all those states which satisfy phi 1 and uh, such that there exists some successor. Okay. So now you consider those states S such that those states S such that S and post of S Okay, post of S intersection T, correct? Post of S intersection T is not empty. Okay, so you consider such states such that post of S intersection uh, not T, and maybe you would also like to have states which are not already in T. Okay, and such sets you would like to uh, I mean uh, you'd like to sort of inductively build this set T, right? T equal to T union this set.
So it should satisfy phi 1.
Yeah, it should also satisfy phi 1, you are right. And S belongs to sat of phi 1. Yes. Okay. S belongs to sat of phi 1, post S intersection T not equal to phi. So take, you should increase the set T by taking union with such set. Okay. So this is what we are doing. So I think this is what it says, that S belongs to sat of phi 1 and post S intersection T not empty. Okay. And so essentially like it's the smallest subset T. So you are, suppose sat of phi 2, it's a subset of T, of course. Like we are going to increase the set T, right? And so it's the smallest such subset T. So you start with just sat of phi T, phi 2, and you keep increasing the set. Okay. And you have the smallest such subset. So at some point of time, you will reach what is called a fixed point. Okay. Where you will see that you don't have any more states which are not in T at this current time, but they uh, satisfy this condition. Okay. So as long as you have such states which satisfy this condition, but they are not part of T, you keep including these these states in your set T, and you actually keep enlarging the set T. Okay, until you no longer find any such state S which will be satisfying these conditions, as well as it's not inside T, right? So that's why it's the smallest such subset T of S. Okay. uh, Now on the other hand, if I talk about there exists G phi, so I say that this is the largest subset T of W, such that T subset of sat phi, right? So this is clear again. Like I think the fact that T has to be a subset of phi, right? T has to be a subset of phi. So uh, whenever I am satisfying phi, doesn't necessarily mean that I'm satisfying that there exists a path which will satisfy globally phi, always phi, right? But if I don't satisfy phi, I'm clearly not in this set. Okay. So to be in this set, its first prerequisite is that I have to satisfy phi. And for all such states which satisfy phi, you will have further conditions, right? So this is like a superset of the set of states satisfying there exists G phi, right? So we are going to remove states from sat of phi in order to get the set sat of exists G phi, right? So um, okay. So we'll see again in more details like how we are computing, but essentially like, so I will start with such a such a T, like first this set, and then if I see that my post S intersection T is empty, correct? And also I should have that S belongs to sat of phi, Okay, so I should consider only such states that S should belong to set of phi, right? And if I see that, so this was already in T, right? So I will first start my T in this form, T equal to set of phi to start with, okay? In order to compute this, first I'll start with T equal to set of phi. Now I will see if for any states, okay, if post S intersection T is empty, then what shall I do? What shall I do if this is empty?
Then we should just remove it.
We should just remove such states from T. Okay. So we should remove from T all such states, all such states, uh, right? So S belongs to T and post S intersection T equal to empty. So we will remove such states, right? So now this is hence like we start with some large set and we are reducing things from it. We are removing things from it. So this will give us what is called a greatest fixed point, or hence this is like a largest subset. So you start from something which is big enough and then you keep removing things in order to reach your final solution. So this is called a greatest fixed point or a largest subset which will satisfy this property. Whereas in this case, we started with something which is like the phi 2 and this was a small set, and in with that and we started adding things to it, and finally we reached this this set T. Okay, so and even if you have, let's say, like, so we are looking at the existential normal form for the model checking, but one can also look at, let's say, if you even if you have the for all formulas, I mean, it doesn't really hurt. I mean, the model checking complexity, it remains the same. Okay, so essentially, like, what you will do here, that along for all successors, right, for all successors you should satisfy phi. So uh, so in order to get this, what shall we do is like, uh, so I mean, so suppose if I have sat of phi, right? And then I'm saying for all successors, uh, I would like to have that they satisfy phi, right? So you just do here this thing, that post of S. So these are those states such that post of S is a subset of set of phi. Clear? It should be a subset. So earlier when we were talking about exists, we were saying the intersection with set of phi should be non-empty. Here we are saying the post S should be a subset of set of phi, right? And similarly, when you have for all phi 1 until phi 2, again you have that it is the smallest set T such that set phi 2 is a subset of T, and then we are saying that S should satisfy phi 1, right? Along all paths, I should have phi 1 until phi 2. Along all paths, I should have phi 1 until phi 2. And then I'm saying that post S should be a subset of T. Okay? Post S should be a subset of T. Clear? Okay? And here again, like for all globally, again, we have this post S is a subset of T. And that's the only difference. Okay? Any question? Any question?
No.
No.
Okay, good. So I think this is an example which we also possibly saw, I don't recall, maybe in the last class, which is like if you are given such a formula, right? So then you see that we have a conjunction, we have this conjunction, right? And then uh, the nodes here, they correspond to some state formulas, right? So there are some state formulas. So you have and, right? So this whole thing is a state formula. Then there exists XA. This is a state formula. This is also a state formula, right? So everything is the nodes correspond to state formula. C negation of C is a state formula. there exists G negation of C. This is also a state formula and so on. So what we will do first, I'll compute sat of A, similarly sat of B, sat of C, right? Then we will compute sat of exists XA, right? So if you have this, from this you can compute this, right? And then we will compute sat of negation of C, right? We can compute sat of negation of C. Then we can compute sat of exists G negation of C, right? And then we can compute exists sat of uh, exists B until exists G negation of C, right? So we can compute this and then the final. So once you have this and you have this, then for the conjunction, you take the intersection of the two sets and then you get the final result, right? So that's how uh, we do the CTL model checking. Okay. So, I mean, if you want to write an algorithm, this is how it looks like. It's fairly straightforward. So you are given a Kripke structure, which is of this form, and a CTL formula phi. Then the set of phi is the set of states such that it satisfies phi. If phi is true, then we saw that it's just a different case analysis. If phi is true, then you return whole of W. If phi is some atomic proposition, then you return the set of states such that A belongs to the labels or the set of propositions which hold in S. If it's a conjunction, then it is you take the intersection. For negation, you have the complement of the set. Exists X phi prime, you just take the post-S intersection sat phi prime. It's non-empty. And this is where I was talking about this iterative computation. When you have exists phi 1 until phi 2, then first you start with sat of phi 2. Okay. So you start with sat of phi 2. So this is the, so some, so we know that all the states which satisfy phi 2 will definitely be there in this sat of phi, correct? And now we are looking for uh, such states which are not, which satisfy phi 1, but they are not already in T. Excuse me. And then you have post of S intersection T should not be empty, right? And as long as such this set, as long as you have such states, okay, there exists such a state. So that means that this set is non-empty. This whole set is non-empty. Okay, as long as there exists some states which satisfy this. Okay, then you actually increment or increase the set T by taking union with this set itself. Okay, T union this set. Okay, so you see that the set T is gradually, it's increasing. So initially we have this T0 is sat phi 2, and what does Ti represent? So Ti here represents the states that can reach sat phi 2 in at most I steps, okay, via a path of states in sat phi 1. Is it clear? Like, so from this definition, so if I have, let's say I call it, instead of T, if I start with, let's say this is my T0, then next I get T1, T2, like this, okay? Then at some point of time, I'll have Tm plus 1 equal to Tn when I'll stop, right? Because I won't have any more states which are, I mean, any more states which will satisfy this condition, right? I may not have. And then I'll have like the Tm plus 1 equal to Tm, in which case I cannot extend or enlarge the set T anymore. and I stopped. Now these are my iteration numbers. So all it says is that now suppose if you have a Ti, it denotes that in at most I steps, you can, if there is a set S which belongs to Ti, then in at most I steps, you are going to see a state which will satisfy phi 2, okay, while uh, satisfying, while going through a path of states which will satisfy phi 1. Clear? Okay, and then finally we return this t, right? This t is this tm or tm plus 1 when it reaches a fixed point. Okay, and this is a least fixed point. This is an example of a least fixed point. Why least fixed point? Because if you look at it, it's like I am starting from something which is a small set, and then I'm enlarging the set. Okay, on the other hand, like suppose I don't know whether you have studied this notion of lattices in MFCS course. Like, so have you studied lattices?
No, not yet.
Okay, so this is something I would expect you to read in your MFCS course. Yeah, so yeah, I mean that, yeah, if you read the lattices, then it becomes much easier for to understand these things. But essentially, like you have, let's say you have um, like um, okay, so you have, let's say for example, um, you have, let's say, a power set of a set, power set of a set, let's say S. Okay, and uh, you can think of like uh, that maybe, let's say, uh, um, you have an operation, let's say, which is like uh, union with, say it's the set S is over, let's say, some natural numbers. You have some uh, union with 1 comma 2, and then whenever there is an operation, if you start with the null set, right, if you start with the null set, then you see that uh, when you do this operation, then just the set 1 comma 2 uh, is of is a fixed point, is, and it's a least fixed point. Is it clear? Like if you just have the operation, suppose you take the power set. So what are the elements of the power set of this set is different subsets of S, right? So you have different subsets of S. So you have different subsets of S, and then you have S union 1 comma 2. Okay, now here let's say the elements uh, in the lattice will be like these elements in the power set. Okay, so these different subsets, and so in the lattice there is a bottom element, which is here you just, I mean, if you consider in terms of the subset relation, so if you have a subset relation, then the bottom element is essentially the null set. Okay, so you have the null set, and then when you do, you start with this bottom element, and then you say, okay, I take phi union 1 comma 2, I reach 1 comma 2. Okay, and now 1 comma 2 union 1 comma 2 is still the same, it's still 1 comma 2. Hence this is my fixed point, this is a fixed point, and in fact this is the least fixed point. Okay, this is the least fixed point. On the other hand, if you consider the full set S, right? If you consider the full set S, then S union, let's say 1 comma 2, that also remains S. So I'm considering here, let's say 1 comma 2, they both belong to the set S. Okay, so assume that this is the case, 1 comma 2, they both belong to the set S. So in that case, S uh, union 1 comma 2 is also S, right? On the other hand, this is also a solution, this is also a fixed point, but this is a greatest fixed point, is the greatest fixed point, right? Now, how you compute something iteratively and what your solution is at the end, it depends on which fixed point you start with. In fact, like often there can be cases where you have multiple fixed points and you are just you are computing something iteratively. And depending on your initial valuation, you may reach different fixed points. Okay, so yeah, I mean, I was under the assumption that the lattices are being taught in the MFCS course. Uh, yeah, I'm not sure about the MFSS, but I thought this is so. Yeah, so and then there are these. Yeah, so but maybe yeah, I okay. I mean, I think we can try to go over this, but I mean overall this is the idea. I mean I can try to cover this in more detail lattices, but I believe you can ask yeah your instructor in MFCS that whether you are going to learn lattices there. Otherwise, I'll try to sort of say a bit more in the in one of the lectures later. But was it clear? Like, uh, did you get the idea? Like, so it depends on your initial valuation, and then you are doing an operation, right? So what is the meaning of a fixed point? So you have studied the notion of a fixed point sometime, the idea of a fixed point,
Yeah.
right? So fixed point of an operator is like you you apply some operator over and over again iteratively, and then when the result doesn't change anymore, that is called the fixed point. So for example, here we are applying some union operator, right? And this is the fixed point, like tm plus 1 equal to tm. Now, whether this is, I mean, so the question is about whether this is the largest, the greatest fixed point or a least fixed point, right? So now I'm saying that if you start from the bottom element and then if you uh, apply your operators, you will reach the least fixed point. On the other hand, if you start with the top element, okay, and if you apply your operators, then you will reach a greatest fixed point. Okay, so that's the thing. Okay, so yeah, and similarly, if you talk about uh, this exists globally phi prime, so you can start with the phi prime, and then here essentially we are uh, going to reach the greatest fixed point because we start with a large set and we remove things from here. Okay, we have been removing things until we reach the fixed point. Okay, compute a decreasing sequence. Okay, so we are starting from a large set and we are having a decreasing sequence, and it represents uh, essentially all. So ti here represents all states from which there exists a path staying in sat phi prime for at least I steps. Okay, so this is what the ti corresponds to. Any question? Is there any question?
No, sir.
Okay, good. So now the complexity of CTL model checking. So you see that CTL model checking is quite simple. So we just look at all the different subsets for each of the subformulas, and then we try to build the entire satisfying set for the whole given formula, right? So all we need to do here is like look at whenever we are computing the satisfaction set of a given subformula phi, right? So all we do here is like for each of these subformulas, we just need to do some kind of graph traversal, okay? And and the complexity is essentially it can all be done in the number of uh, edges in that Kripke structure, okay? And since we are doing this bottom-up traversal for each of the subformulas, so it gives us for each subformula we have uh, this kind of uh, computational uh, like this is the complexity. And since we have like let's say the number of subformulas is or if is of the order of size of uh, the formula phi, so the complexity of time complexity of CTL model checking is this much, right? Big O of the size of the Kripke structure times the size of the formula, okay? Hence CTL model checking is in polynomial time. So we have seen that LTL model checking was, what was the complexity of LTL model checking?
P-space, right?
It was p-space complete.
P-space complete, yeah.
Right? Whereas CTL model checking can be done in polynomial time. Now one should then ask the question that what is the difference? Like, I mean, why is it the case that CTL model checking can be done in polynomial time, whereas LTL model checking is p-space complete? What is the fundamental difference? I mean, is there any difference as such, or there is something which is more fundamental? What is the main thing for which it's like that LTL model checking it was essentially like it was p-space complete, whereas CTL model checking you just look at the Kripke structure and you can do it in polynomial type. What is the fundamental difference? So if you recall in LTL model checking, what do we do? You essentially you compute an automaton, right? You compute that GNBW, right? Generalized non-deterministic Bushy automaton, and which can indeed be translated to an NBW. And then you take a product with the Kripke structure, right? You consider phi, you consider the complement of the phi, negation of phi, and then you construct an NBW, and then you take a product with the Kripke structure. But here we are not talking about any of these automata construction. So what is the basic fundamental difference? So I would let you think about this, and so that is something you can think over and we can discuss sometime. Okay. So, okay. So now one thing we would note is that, or maybe we mentioned that it's not necessary that every formula in CTL can be the properties that can be expressed using a CTL formula can also be expressed using an LTL formula and vice versa. Uh, does it, is it clear, the statement? So every property, like you talk about a specific property, it's not necessary that this property can be expressed using, uh, I mean, so what I'm trying to say is that every property that can be expressed using LTL can also be expressed in CTL and vice versa. So do you recall, like we looked at some property like this, that there was some property we saw which one can express using CTL, but there was no LTL property, no LTL formula which could express that property. Do you remember? So we saw something like this. What was such a property? What was such a property? Do you remember? Like some example of a property we saw which can be expressed using CTL but not in LTL. What was such a property?
Like being able to reach the begin state
Yeah.
when
Right.
there were, yeah.
Right. So it was like, so we had something like the following, that I mean, it is possible to correct. So I think this is the, yeah. So one, right? So this says for every computation, it is always possible to return to the initial state. So you see that indeed, if you talk about this, it is always possible to return to the initial, sorry, to the initial or begin state. Now you start from here, whatever be the computation. So you start and then you stay here forever. But it is possible, it is always possible to reach the begin state. Correct? On the other hand, like if I say that it is always possible, like I mean, the thing that I can uh, think about is like globally eventually begin. Now, this is not true in general. Uh, it is, so what does globally eventually begin say? It is always the case that, so you consider a path, right? So you come here and then you loop here. So you say begin p omega, this path, begin p omega, it's written here. Okay, begin p omega, this does not satisfy this property, gf begin. Is it clear that it does not satisfy this property gf begin? Okay, is it clear?
Yes, sir.
It's okay, right? Like begin p omega does not satisfy that globally eventually begin. This path does not satisfy. But on the other hand, if I talk about like it is always possible to return to the initial state, right? This one can express using CTL. So how, what would be the CTL formula corresponding to this? Can someone suggest what should be the CTL formula?
There exists a path from that state such that it can
Yeah.
reach the begin
What
state.
should I write here? Along all paths, suppose I start from here. Okay, this is my initial state. So what should be the formula corresponding to this? You are right.
For
There you have to say that there it is always possible, like there exists a path. Okay. So along all paths, huh?
globally,
Yeah.
for all eventually
Along all
begin.
paths, eventually, along all paths,
No, there exists a path. For all globally,
uh,
there exists
there
eventually.
exists a path. You are right. There exists a path. Okay. Along all paths, it is always the case that there exists a path such that eventually I can reach begin. Clear? Okay. Along all paths, it is always the case. So even if you consider this path, along all paths, even if you consider begin p omega, right? Okay. So then this, so in begin p omega for this particular path, so let's consider this part, right? So the path is begin p omega. Now, uh, now let's consider in if this holds true. So it is always the case, it is always the case when you are here, it is always the case that there exists a path such that eventually you can reach begin. Correct? It is always the case that there exists a path such that eventually you reach begin. Right? So once I have, so the quantification is over all paths, right? Now I'm saying that now consider this path, right? So this, so I have gotten rid of the path quantifier now. For this fixed path, I'm looking at only this part, okay? Which says it is always the case for this path, it's a path formula, right? It's a path formula. It is always the case that there exists a path such that eventually I can go to begin. Clear? So indeed, this is a CTL formula which can express such a thing, but no LTL formula can express this. Okay, good. Okay, so we'll see other properties also that one can express using CTL, but not using LTL and vice versa. So we say that CTL formula phi and an LTL formula tau to be equivalent if for every Kripke structure we have that K satisfies phi if and only if K satisfies tau. Okay, we call a CTL formula phi and an LTL formula tau to be equivalent if and only for every Kripke structure K we have that K satisfies phi if and only if K satisfies tau. Clear? Uh,
Yes, sir.
Yeah.
the definition is clear. Like when do we say a CTL formula and an LTL formula to be equivalent? If it is the case for every Kripke structure, all the Kripke structure which satisfy phi should also satisfy tau and vice versa, then they are equivalent. Now there is a result which says that suppose phi be a CTL formula. Okay, suppose phi be a CTL formula and let's say tau be an LTL formula obtained by eliminating all path quantifiers from phi. Okay, so phi is a CTL formula and tau is an LTL formula which is obtained by eliminating all the path quantifiers from phi. Okay, so the definition of tau is clear. Now it says that then either it is the case that phi is equivalent to tau or there doesn't exist an LTL formula equivalent to phi. Okay, so we'll not go through the proof, but I think the statement is clear, right? So um, for example, like suppose we have this thing for all globally there exists eventually a, like this is what we saw a little a while ago. There exists f begin, right? Now if you remove all the path quantifiers, so you get gfa. Okay, so for this formula the theorem says that for this formula you get the corresponding LTL formula. Either they have to be equivalent or for this there doesn't exist an equivalent LTL formula. Clear? So indeed, since you can show that these two are not equivalent because there exists such a Kripke structure where you can show, it just follows from this theorem that for this formula there doesn't exist an equivalent LTL formula. Clear? By looking at this result, is it clear?
Yeah.
Yeah, right, that indeed for this CTL formula there doesn't exist an equivalent LTL formula. Okay, now let's see. Here I have some more examples. So I say for all paths, okay, eventually for all paths globally A. And if you consider the LTL formula FGA, right? If you are given this, then by the above theorem, if you have an equivalent LTL formula, it should be of the form FGA. Now you look at this Kripke structure, okay? So can you tell me which Kripke structure, uh, which Kripke structure, sorry, which formula is satisfied by the Kripke structure here? This Kripke structure, does it satisfy this or this? I mean, clearly, I mean, since I'm saying they're not equivalent, it's not going to satisfy both of them, right? So can you tell me which one is satisfied? The Kripke structure satisfies the LTL formula or the CTL formula?
It satisfies the LTL formula.
Sorry, I could not hear you.
It satisfies the LTL formula.
It satisfies the LTL formula. Like either, so what are the paths? The paths are like either you stay here or at some point of time you just go here. In both the cases, it satisfies eventually globally A, right? If you come here and then come here, after some finite amount of time, you are coming here, right? And then you say satisfy globally A. Or you are always staying here, in which case also you are satisfying globally A, eventually globally A. Okay. But what about this one? Why is this not satisfied? For all paths eventually, for all paths globally.
If it stays in S naught, then like it won't have the like It's not going to be globally
Correct.
eventually.
I mean, so if it is like this along all paths, so suppose you consider this S0 omega, this path S0 omega, then what happens is like eventually for all paths globally A. It's not true because eventually for this, there is no such point such that along all successors you will have A always, because there is always such a successor, right? Such that where you have A is not satisfied. Clear? Is it
Y-
okay?
Yes.
Okay. Any question?
So I guess there exists quantification in the eventually in LTL, right? That's the semantics. So
No,
everything which is there exists before an F in the CTL formula.
no. Whenever if you have an LTL formula, if you have an LTL formula phi, say LTL formula phi, in the CTL formula, you will always read this as for all phi, because the Kripke structure will satisfy the formula phi if all paths of the Kripke structure satisfy as phi, right? The model checking problem is like the traces, right? So we saw this traces of K should be a subset of words of phi. This is how it is, right? So all the traces for all paths of this, right, it should the uh, satisfy the formula phi. Okay, whenever there is an LTL formula phi, there is this thing. So the difference, see, I mean, this difference between CTL and LTL is that if you see, CTL has an inherent branching kind of a property. Like it says that, for example, at different points in time, at different, suppose you have this thing, right? So you have S0, 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 A, you are seeing. But at different points in time, what are the branching structure? In the sense, what are its capabilities? What are the capabilities that it has? What are the capabilities that it has? Like, can it uh, can it do something which can uh, lead to a state where, I mean, in case of LTL, you are looking at the individual traces and these properties, whereas in CTL, you also look at what is there happening in the middle and what are its potential things that it can do in the middle. Does it make sense what I'm saying? Like, so for example, you are saying for all paths, eventually for all paths globally, right? S0 omega. So this is a path. Okay. So now for this path, you look at this path formula. Eventually, for all paths globally A, right? So you look at for all the points, if there exists some point such that all its capabilities, like in the sense that all the things that it can do in future, it can do have an A here, it can have an A here. For all its branching, it will be able to do an A. Does it make sense? Like, so the CTL in some sense, it talks about the branching properties really. Like, so for example, at different points in time, what are its abilities? Whether it can do the A along all the paths. Make sense? Along all
Hmm.
the paths,
Makes sense. Yeah.
right? So you come and then you see that you actually probe the, I mean, what somebody can also call it like the the features that you can see across all the different branching uh, all the different branching like uh, I mean the branching evolution, right, at different points in time, and what are the properties that you could see if even if you are branching at these different points in time, right? So that's what CTL has, which LTL somehow doesn't capture. Hmm? So because here we are saying that eventually for all paths, I should be. So here, for example, when I'm here, like I'm just this S0 omega for all paths, like at every point, I'm seeing for all paths, this path as well as this path. Okay. Like at every point, this path as well as this path, whether I can I can satisfy this globally, okay, which somehow LTL doesn't capture. LTL just starts, looks at the paths individually, like it has all the paths, and looks at the paths individually, right? So that's why if you say eventually globally A, yes, eventually you look at this path, eventually globally A. If you look at this path, eventually globally A. I mean, this is true, but it doesn't talk about like looking at what are the properties it can do at every point in time, at the different possibilities that can be there, right? The different things that can happen because of the branching. So that somehow LTL doesn't capture. Okay, right. So now, if you look at another formula, uh, what about this one that so if eventually A and next of A, okay, eventually A and next of A. So again, does the LTL formula, is the LTL formula satisfied by this Kripke structure which is given here? Eventually A and next of A. So this,
No,
what is the answer?
no, it doesn't satisfy because like S0, S3, S4, we can just keep looping.
S0, S3, S4. So this doesn't satisfy. So if you say this
Yeah.
loop, S0, S3, S4, omega, correct? Does it satisfy eventually A and next of A?
That is S4
Oh
and
wait, yeah, it
S0.
does.
Yeah.
What?
Sorry, it does. My
It
bad.
does, right?
Yeah.
Because you have like in this path, eventually you reach here and then you have A and next of A. It satisfies, right? And it also has to do like for every path. Like, so whenever it's like this, like essentially intuitively, it's like for all this formula phi. The other path is like this. And this also satisfies A next of A, right? So this also satisfies. So indeed, this LTL formula is satisfied. Now, what about this particular one? This particular CTL formula. Is this CTL formula satisfied by this Kripke structure?
Yes, again, because both the
Because of what?
paths.
Is it satisfied? Is it satisfied? So what about the path S0, S0, S1, S2 omega? Does it satisfy this formula?
Yeah, the
For all
issue
paths?
is S3 is not an A, and we have a for all next. So
Yeah. So you see that it says S0, S1, S2 omega. So what do you think? Like anybody else wants to suggest something? Like, does this satisfy this formula? So this path. So for all paths, you have to satisfy. Now I choose this particular path. So if this path satisfies this path formula, does it satisfy this path formula? S0, S1, S2 omega. What do you think?
The for all not it's will
Sorry?
be an issue.
Sorry?
Next away, it's just towards S1, one way towards S3. So
Uh,
that won't be satisfied.
that won't be satisfied because you have like, so eventually A and negation of and for all xa, right? So suppose eventually a can be satisfied along this path either here or here. If you satisfy eventually a, then for all paths next a is not satisfied, so clearly s1 is ruled out, right? You have to now consider this state. So eventually a and for all paths next a. So this path, of course, here you have a satisfied, but for all paths here you don't have the a being satisfied, you have a phi. So indeed, this particular path, that it doesn't satisfy this formula. Clear? Okay. So again, we don't have a corresponding CTL formula. Okay. Good. So now indeed we can sort of saw this, right? So we saw this, that FGA and for all F for all GA, they are not equivalent. So it says that FGA can be expressed in LTL but not in CTL. I mean, you can prove this more elaborately, all these things, but we have more or less we have an intuition, and this is something we saw, right? It is always possible to reach that begin state which we saw earlier, right? It's essentially that kind of a formula. For all globally there exists eventually a, right? So this is that begin state. It's always possible to reach the begin state, so can be expressed in CTL but not in LTL. Now on the other hand, you can actually argue that GFA. Okay, so what is this GFA? It's like the Bushy property. It's not really a it's like a Bushy property, right? So GFA, it's like a Bushy property, whereas FGA is like a Kobushi property, right? You understand this thing. You recall like what is Bushy and what is Kobushi, and you remember, and GFA is like a Bushy property. Why is it so? Why do I say that GFA is a Bushy property?
Because at any point we wanted to eventually come back to the good state, so
Yeah.
globally eventually.
And FGA is like a Kobushi property. Why is that? Why is FGA?
Because like after a point we don't want to go to any
correct
non-good state. We want to stay in the good state.
Right. Okay. So that's so yeah. So and one can indeed show that GFA is equivalent to this, and this can be expressed in both LTL and CTL, and so this is how LTL and CTL they look like. So you have some formulas in LTL which cannot be expressed in CTL and vice versa. And there can be some properties which can be expressed in by both. Okay. So in general, LTL and CTL are incomparable. And so there is a logic which encompasses both of them. It's called the CTL star. Okay. So what is the CTL star? There the alternation of state and path formulas in CTL is relaxed in CTL star. So CTL star includes both CTL and LTL strictly, in fact. Okay. So so let's look at the CTL star syntax. So the state formula here, it looks like just your CTL only, right? You have phi1 and phi2 negation of phi exists psi. So this is in the ENF, right? In the ENF form, exists psi. You can also have the for all psi can be expressed using exists formula. And the path formula here, you see, is in fact like there are many changes in the sense that we allow negation on the path formula, and in fact that a path formula can also be a state formula in itself. Like, so what happens in this case? So suppose if you have there exists, now you can have there exists phi, correct? and the psi can be replaced with a phi. So you can have there exists phi, and um, this phi can be again phi 1 and phi 2, and like, or you can have, let's say, x of psi, and the psi can be again a phi, right? Or correct, I mean x of psi, and then you can have uh, x of phi. So for example, like let's say if you have uh, so suppose if I have uh, there exists uh, I want to say uh, f g a. Okay, so let's just check if this is indeed a valid CTL star formula. Okay, so how will it look like? So you have, there exists a psi, right? So you have this rule, and now psi is of the form uh, psi 1 until psi 2. So the f is like an until, right? So you can have, of course, this is there. Then it's like true until, so we are saying true until uh, globally A, correct? Now the psi itself is like um, um, so how do I get this globally A? So let's try to see. Um, so this is a path formula, correct? The psi 2, this is psi 1. So there exists, so let me try to write. So there exists, then this is like true until globally A. Huh? Yeah. So this is just uh, this is a state formula, right? There exists, after that I'm saying this is true. So there exists psi. Okay. So it's like this. So I have phi 1 until psi 1. So here I have like a psi 1, and this is psi 2. Okay. Now psi 2. So how can psi 1 be be a state formula? It is perfectly okay here. See, that path formula itself can be a state formula. So you apply this rule, okay, this rule, and hence you get a true is a state formula, right? So you apply this rule essentially to get this here, and psi 2 is anyway a path formula. So you have globally A, correct? So you have again globally can be written using the until, correct? So the negation of the until and so on. So is it okay? Like, I mean, indeed, if I have a formula like this is not allowed in CTL, but this is allowed in CTL star. Was this clear? Any question? Was this clear?
Yes, sir.
Yes. So, but this is, you see that this is not allowed in CTL, because you have in CTL, for example, you would have like whenever there is an until, you have a phi 1 until phi 2, where phi 1 and phi 2 have to be state formulas, right? Whereas here you allow them to be path formulas, right? And then these path formulas themselves can be state formulas. That's the thing. So CTL star, indeed, it captures these LTL formulas. In fact, any CTL star formula, any LTL formula rather, any LTL formula phi is equivalent to uh, CTL star formula of the formula for all phi. That's all. So if you're given an LTL formula phi, you can always construct a CTL star formula which is of the form for all phi. Okay. And now if you talk about, yeah, I think it's, yeah. So any CTL formula is also a CTL star formula. LTL formula psi has an equivalent CTL star formula of the form for all psi. And CTL star is strictly more expressive than LTL because all the LTL formulas you can express with in CTL star, and on top of that there are these CTL formulas which you can also express using CTL star. And CTL star is strictly more expressive than LTL, and similarly also more expressive than CTL as well. So for example, like if you consider such a formula for all FGA and for all globally exists FB is not expressible either in LTL, or in CTL. It's not expressible. Why? Because you see that FGA cannot be expressed in CTL, right? And this part is not expressed, cannot be expressed in LTL. Sorry. So their conjunction cannot be expressed in like either CTL or in LTL. So one part cannot be expressed in CTL, the other part cannot be expressed in LTL. But this is a valid CTL star formula. So which means that there are properties which can be expressed using CTL star, but not in either LTL or CTL. So CTL star is strictly more expressive than both LTL and CTL. Okay. So yeah, so we will not go through the CTL star model checking in detail, but essentially the CTL star model checking, I mean, you can try to read it yourself. It combines both the algorithms of LTL and CTL, and essentially like the complexity, it's again p-space complete. The CTL star model checking is p-space complete. And I think the p-space hardness is clear enough. It's like the hardness follows directly from LTL model checking. But what is interesting is the upper bound, that why it is also in p-space. So this is something you can try to read yourself. And essentially like you have this kind of, so essentially, so this, if you recall, this comes from the, I mean, here I'm using K here. So yeah, I wrote T for a transition system, but essentially K for a Kripke structure. So this is the size of the LTL. Sorry, this is the complexity of the LTL model checking, right? And so, I mean, pretty much, yeah, this is the complexity of the LTL model checking as well. Okay, and that is that. So the CTL model checking is p-space complete. So as I said, sorry, CTL star model checking is p-space complete. So as I said that the hardness is easy. It follows directly from LTL model checking. So the interesting thing is to look at the upper bound, right? So, okay. So this is this, and next time I'll end here. Next time we'll start with something called bisimulation. So which is about some sort of behavioral equivalence between Kripke structures which satisfy the same set of CTL formula. Okay, so we have looked at the notion of stress equivalence, or like the language equivalence, like in different contexts. For example, in automata theory, when you study, you have seen these like two automata, they are equivalent if they accept the same languages, right? And whereas, as I was saying, that in CTL, it's somewhat like it's doing something more, in the sense that it's also looking at what are the abilities at the intermediate points, like what all things it can do, right? At some point in the middle, whether it can do like across all the successors, whether it can do an A or like, so this kind of things LTL doesn't capture, right? This branching kind of properties. And there are, so essentially if you can say that, then what are the notions of equivalence across these transition systems if they satisfy the same set of CTL formulas, right? What kind of, are they equivalent these transition systems, the Kripke structures are the equivalent in some sense, right? So bisimulation is a notion of equivalence, which is stronger than language equivalence, and which sort of is a behavioral equivalence which uh, we would see if, for example, these two Kripke structures satisfy the same set of CTL formulas. Okay, so this is the thing. So we'll look at this by simulation in the next lecture. So any question before we end?
We had this non-counting languages based characterization for LTL.
Right.
Yes.
Yes.
Is there a similar one for the intersection between LTL and CTL?
So intersection of LTL and CTL. Okay. Yeah, I am not aware of. Yeah, I'm not aware of like what sort of things. That's a good question. Like what sort of properties essentially like one can think of for, I mean, what sort of properties are captured by both LTL as well as CTL?
Yeah. Because
Yeah.
there is this algebraic characterization along the lines of the non-counting languages, yes,
Yeah.
for LTL, but
Yes.
might be interesting to look at.
Yeah. Yeah. I don't know. Yes. Yes. Yeah. Okay. No, I don't know like what are the, I mean, what are the characteristics of these properties which are captured by both LTL as well as by CTL. Yeah. But yeah, it would be good to think about that. Okay. Okay. So let me stop the recording.